Okay, yeah, whatever. I'm going to put out an assignment soon for an abstract, just a brief abstract of. It doesn't have to be what's going to be in your final report, the abstract, but what I want in the abstract is kind of, here's what I plan on doing types of things, and it can change a lot once you get into it. Like, it can even completely reverse itself. So your abstract can start off saying, I'm going to show that this is true, and then as you work with it, you might find out that that's not true, and that's all right. I just want something that kind of says the general gist of what you're going to be doing. Okay, so deadlocks is that's pretty much what I want to know in general is what you're doing. But when we get to the abstract portion, put some focus on it because since it's such a broad topic, just narrow it down. Everybody else has kind of given me examples of kind of where they're going with their project, how they're going to narrow it down. So just basically put something like that into a brief abstract.
And when do you go?
I'm going to put an assignment out for the abstract, so that'll probably be due like Tuesday.
No, the project.
The project, there's a progression of things that are going to be due, but you're going to need your slides and presentation. Obviously, are going to need to be ready for the presentation, which is the last, I think, 2 class periods in the calendar are for presentations, and then the final write-up of the project, as well as I'd like to see any code and things that you did. All of that package is going to be due on the day of the final, so that I can get both the finals and those graded and submitted. But yeah, this first part of the abstract is just to lock everybody in. I'll probably do one other thing just so that I can see some progress to make sure that everybody at least has started some sort of experiment or code or something, so that it's not all done like the Friday before or the Monday before we start doing presentations. Because I am going to expect that everyone be ready on that Tuesday to present. In other words, everyone's going to give me their PowerPoint, like their presentation materials and things like that before that Tuesday, so that nobody kind of has additional, it's so that it's fair for everyone. And then I'm just going to randomize what order we present in. Okay, so let's see. Today I'm going to finish up just the little last half of that of the security chapter. What's that? Not this coming Tuesday. It's I think it's even after Thanksgiving. There's a week of class after the Thanksgiving break. Okay, I think it's that week of class that is. Oh, actually, I guess. So we're going to be covering the two case studies this week and next week, Linux and Windows XP, and then we have break. I highly recommend that everybody gets started on their project so they don't have to do much of it over break. 28th and 30th will be presentations, and then next week for that is, I actually have 2 weeks scheduled. No, that's the same. Okay, 28th and 30th, and then the week after that I believe is finals. Does anybody know what our final day is?
I think it's on the 12th.
On the 12th.
I think.
Oh, the 9th through 15th. Yeah, that sounds right. Okay. Oh, I can. Okay, great. That means we have plenty of time. So the presentations will probably be the 5th and 7th. Cool. So I'm going to spend actually a little bit more time on security today then. I realize I get a little bit more buffer for topics, for the lectures. So the day of the final, you'll have a final as well as that'll be when all the materials are due. Your write-up and then any code that you have that you can submit to me as well. But the idea is that by the time the project presentations come around, you're mostly done as far as at least the coding and any experiments that you're running, any pretty graphs that you're going to make for performance or something like that. All of that will be done by the presentation day, and then that way, the only thing left is the write-up, which sounds like the hardest part, but actually once you get all your data, it's really just going to be reporting on that data. Okay? You are going to have a little bit of background on the topic, so you may need to do a little bit of reading and pulling from both your book and any outside sources and whatnot, so that you can have a little bit of write-up for the background explaining why you did what you're doing and that kind of thing. But for the most part, the experiment part, you should really get started on and start working with so that you can run into some issues, whatever issues you're going to run into, and we can talk over it and get through it. Okay, security. So we left off last time briefly talking about symmetric encryption, right? So, what's the basic idea behind symmetric encryption? Symmetric encryption. What's the idea of encryption? Hide stuff. So hiding data from people who aren't supposed to see the data, right? So, what's the basic idea behind symmetric encryption? What's that? No. You take data, and what else? What other components do we need besides the data? We need a key, data, and what? An algorithm. Take a key, we take the data, we send it through the algorithm, we get encrypted data, usually called the cipher. Okay? To go back the other way, we take what? Encrypted data. What else? Key. What's significant about the key? Right, that's how we're going to unencrypt it, but what's significant about this key in particular in this system? That it's constant, right? It's the same as the key you use to encrypt the data. Okay? That's what symmetric means, okay? Is that we use the same key to encrypt as we use to decrypt. Okay? So we take the same key, we take the encrypted data, we send it back through the algorithm, maybe a different algorithm, and then it comes out as the clear text, okay, the original data. Okay? So I asked you the clever question of if that's symmetric encryption. What other type of encryption do you think there is? Asymmetric, right? So the opposite of that, right? All right, if symmetric encryption, what was the symmetrical part of symmetric encryption? What part was symmetric? The key, right? So in asymmetric encryption, what do you think? Different keys are going to be used to encrypt and decrypt, okay? So, asymmetric. Okay, this is a more. It's not a better type of encryption. It does use more modern techniques in encryption, but it's not better. Okay, it's a different style of encryption, and you need to really understand that, because a lot of people, when they encounter encryption, they see symmetric, they see asymmetric. They see asymmetric as new and it has all kinds of nifty features, and they think of it as better. It's not. It has its its advantages and disadvantages compared to symmetric. It's just a different technique. So as we pointed out, the symmetric in the other type of encryption is we use the same key to encrypt and decrypt. In this style, what we will do is we'll use a particular key to encrypt and a different key to decrypt. Okay? So we call the encrypting key, we will call the public key. Okay? Why do we call it the public key? Because we'd like for the public to have that key so they can encrypt anything they want to send to us. Okay? We don't need to hide this key. Okay? The reason being is because we use a separate asymmetric key called the private key to decrypt. So this we do want to keep a secret. Okay? So the idea is this. I give you, the public, my public key. Okay? So if you want to send me a message, you can take that public key, use an asymmetric algorithm, and encrypt data. You'll have encrypted data, but the only key that can decrypt it is the private key, which I hold. I'll get your encrypted data, I'll take the private key, send it through an algorithm, and get back to the clear text. Okay? So, as long as no one has the private key, no one can decrypt. So, even you, the sender of the data, after you encrypt it, you can't even decrypt it. Yeah?
And in that case, why we need a key in the first place to encrypt?
Because that's what creates the relationship to the private key. This private and public key are related. So you have to have something unique about what they're using to encrypt. What I'm saying is if you're saying we don't need a public key, okay? I can just encrypt data. Well, what's to say that any private key can't decrypt it at that point? If there's no piece that's unique to what you're encrypting, there's no way for it to be unique to my private key to decrypt. You see what I'm saying? There has to be a key involved. If not, if it's generic in some way, that means decrypting is generic in some way.
That is identifying.
They're actually mathematically related, and that's how these algorithms are designed. There has to be a relationship between the private and public key. Okay? And the idea is that there's some relationship between these keys that make this behavior occur. And the behavior is you can encrypt with a public key and you can decrypt with a corresponding private key, and nothing else will work. And that's key. And that's what's difficult. That's the difficulty of designing these algorithms. Is creating a relationship like that is very difficult. Okay? Creating symmetric algorithms is also difficult, but that's kind of why this was kind of discovered later, this asymmetric style of okay? So, again, the key here is that you need to, also in all of these algorithms, the algorithm needs to be able to be published. Right? You need to be able to share the algorithm because everybody's going to be using that algorithm. Okay? The important thing here is that you've distilled most of the secrecy into the key. In other words, if the key is secret, the data is safe. And by safe, I mean it cannot be decrypted by someone who's not supposed to decrypt it. Okay? We're not quite as concerned with people being able to encrypt data. Right? We don't mind if people over-encrypt. They encrypt stuff and, and we're not really, that's not really a breach of confidentiality that we're worried about, right? What we're more concerned with is can they decrypt it? Okay? So, in what ways is this style of encryption superior to the symmetric style? Okay? So there's two different keys. That doesn't, that's just more to keep track of.
Well, there's certain data, right? So one user submits one big chunk of data, other user submits one big chunk of data. How do you know which chunk is whose? So, wouldn't there be, like, it says the individual users, right? Wait, is the private key the same,
For what?
like for every user?
You mean, do two users have the same private key? Absolutely not. No.
So I could label like the first one, like the private key somewhere and it could have like the first chunk of data is this user. You know, so it knows where to get it and knows where to decrypt it. So, I mean, that's an advantage. The fact that everybody can store their own data and still get it back without using anybody else's.
Well, I guess, how can we do that where we can't do that with symmetric?
Symmetric, there's only one key, right?
Well, there's symmetric, but symmetric, there's one key between the person encrypting and decrypting. That doesn't say that I can't create a symmetric key that I use to communicate with you, and I have a symmetric key I use to communicate with you, and have individual symmetric keys I use to exchange with each other. In fact, I'd probably want to do that, right? Why? Because if I'm using two symmetric keys to talk to two different people, I mean, if I'm using the same key to talk to two different people, what other thing am I implying about that encryption? If I use key A to talk with two different people, they use key A to encrypt stuff to me, I use key A to decrypt it, and vice versa. That's, yes. You can see the data that the other user sends to me, and the other user can see the data you send to me. What's that? What I'm saying is that's why I'm saying you want to use two different keys for two different people. Right? But if I use key A and key B, that relationship no longer applies. Right? Now, but what's, yeah. Sure. Okay, let me draw some of it up. Okay, there's three users involved. Okay? A, B, C. Okay? So, if I want to encrypt and decrypt data between two users, I need a key. Okay? So let's use we use key 1 to talk between A and B. And if I'm not careful and I use the same key to also talk to user C, right? What I'm implying, maybe accidentally, is that B can now read the traffic going, or the data going between A and C now. Why? Because it possesses key 1. Right? Now, if I want to be more careful, I can use key 2 when I talk between A and C. At this point, any of the data traveling between A and C can no longer be decrypted by B because it does not possess key 2. But user A has key 1 and key 2, and it needs to in order to talk to both. Okay? So, if B wants to talk to C, what would I want to do there? Right? I want a separate key to talk between them. Okay. So, that's how I'd set up a system to talk between these three users. How would I do that with asymmetric encryption?
They would all use the same public key on the front end. They would all have different keys on the back end.
Let's use numbers. Okay, so to make a key relationship, what I'm going to say is that's the symbol with a 1 will be the private key 1. One prime will be public key for 1. So, let's assign keys. Now, explain your scheme utilizing those terms. Okay, so 1 prime. Who needs 1 prime? A, B, and C. Okay. So I'm going to give 1 prime here, 1 prime to C, and 1 prime to B. Now, this implies that I need 1, private key 1. Where should I put that? What can I do now with just these keys assigned how they are? Can decrypt. A can decrypt from B and C. So, notice what's interesting about this. Notice my arrows only go one way. Okay. Do I need a different key, a different, like 2 prime for C to talk to A? Why not? That's what I needed before in the symmetric system, right? I needed key 1 between these and key 2 between A and C. Why do I not need a different public key for C to talk to A? More importantly than that.
Just they using 1 prime for a public?
Yeah, they're both using 1 prime, but why do I not need a different key for C to talk to A? What was the problem with using symmetric key 1 between A and B and symmetric key 1 also for talking between A and C? What was the problem? B and C could decrypt each other's data. Do we have that scenario here? Can B decrypt data that C sends to A? Why?
Because B doesn't hold 1.
Doesn't hold 1. Doesn't hold private key 1. Okay? We actually don't need A to have this 1 prime. We can. We don't care who has 1 prime. Right? But we don't need it. Okay, so now we're started. Notice we have some arrows going up towards A. So, complete the system.
So, send the other way.
Okay, A to where? Okay, let's say A to B. How will we do that?
A needs 2 prime. And
3 where?
3 prime.
A gets 3 prime.
C gets 8.
We're not done yet. Okay? Notice that. We draw these arrows. Key prime is the source. Key is the destination. Anytime you put in this X prime going to X, you create one of the lines. Okay. The interesting thing about all this is that notice all the primes, 1 prime, 2 prime, 3 prime, All of these are public knowledge, right? So you don't actually have to store it. You can actually just ask for it when you want to encrypt to somebody. If I want to encrypt to you, I can just say, hey, can I have your public key? And you can give it to me. Why do we have to worry about someone seeing that key when you give it to me? No. We don't, because no matter who steals that key, what can they do? They can now encrypt to me. That's it. Okay? There actually is a separate problem, and the separate problem is the danger is them altering the key. Okay? So, this is how we do this system. Okay? Each user has a private key, and then they publish a public key. If you want to send something to the user, you use their public key. Okay? So, this is different from the symmetric system. Okay? But we're trying to accomplish the same thing. Okay, here's the bonus question. What if I told you that asymmetric encryption is very slow compared to symmetric encryption? Okay? What I mean by this is, if you wanted to send me a huge file encrypted, I'm saying that it is very inefficient for you to encrypt that whole file using an asymmetric system to send it to me. Okay? So, the idea is this. I want to send you an encrypted file, but our resources don't allow us to use this asymmetric system to encrypt the whole file. How would you solve the problem? You have two techniques available to you, symmetric and asymmetric. So obviously, me saying that you can't use asymmetric to encrypt the whole file, right? What are you going to use to encrypt the whole file? Symmetric. That's the only other technique we have, right? So we're stuck with that, right? We want to encrypt the whole file using symmetric, but what's the problem? We have this problem of getting key, like the symmetric key, to each other, because we can't just send the symmetric key to each other, right? Because what if somebody grabs that key? So what do? Using what? Use asymmetric encryption to transfer the symmetric key. How can we do that? Well, E is the bad guy. Okay, they're watching stuff that A and B give to each other. Okay. If I have a file, okay, if I take a symmetric key, I use a Roman numeral 1 for a symmetric key, okay, and I encrypt the file using symmetric encryption. Okay? I can't send symmetric key 1 over to B. Why? Because E will watch it and steal it. That way when we send the file, we can use that key to decrypt it. Right? No good. Can't do that. So, what do I do instead? Well, what I do instead is I generate a private key 2. From there, I can create 2 prime. And what do? Oh, sorry. I have B generate 2. And from there, B can generate 2 prime. Okay? I send 2 prime over to A. Do I care if E sees 2 prime? No. All that would mean is that E could now encrypt to user B. We don't care about that. So, when A receives 2 prime, it will asymmetrically encrypt symmetric key 1 using 2 prime, and what comes out, well, is a little encrypted I encrypted by 2 prime. I send this over to B. What does B do? Uses private key 2 sends that through asymmetric, actually decryption, and what comes out? Symmetric key I. Now, A and B both have symmetric key I, and it never went across this area where the bad guy was sitting. So what does it do? Now A can send the file encrypted with key I. This gets over to B. You take the file, and you take key I, send it through the symmetric decryption, and then you're back to the file. Okay? That general idea right there explains the bulk of crypto systems in the world. Okay? Everything from your SSL that you use to go visit like Amazon.com or your bank. Okay? Things like, I don't know if you've heard of PGP. Pretty good privacy. It's an encryption system. They have email systems that encrypt. They have all manner of things that are for encryption. The bulk of them use this technique in all the various forms.
Key for 2 prime and 2. How they going to make this? And when you decrypt the key, which is private key, how the other party will know what's the
Tell them. You say, hey, here's 2 prime. Encrypt stuff with it and send it to me. I'll decrypt it with 2. I don't have to tell them to. I just say, here's 2 prime. Use this to encrypt things to me.
Oh, so this part is, and who receives, he actually sent first the.
I mean, you can agree upon it before you start any of this, or you can do it right before you do it. You know, all you do is say, use this key to encrypt things if you want me to decrypt them.
So the important thing is that B actually generates the keys. If A did it, it's still the same problem.
If A generated the 2 prime,
Yeah.
yeah. Whoever's receiving needs to give out their public key. Now, the other thing is that you're welcome to, here we had A generate I. Okay? You could do it the other way. You could have B generate I, get the public key from A, right, a 3 prime from A, encrypt the I and send it this way, and then A can use the decrypted I to encrypt this data. Either way, it doesn't matter.
That's less communication. B
No. Well, it's about the same communication, but the problem is A could have been encrypting the file with I the whole time while this negotiation was taking place. But that's just a matter of who wants to send first. Okay? There's actually an even more clever system than this that uses the same idea. where the asymmetric encryption is a little different. Okay, but that's just details. A little more advanced. For those of you interested, it's called Diffie-Hellman asymmetric encryption. I believe there's a cryptography class in the math department, and then there's also a data security class that Harrison teaches. I don't know. I know there's a lower level security class, I think, and then there's data security, which is an 8,000 level class by Harrison, and then I think the actual cryptography class is a math class. Well, it should be, because I mean it is very math. This is the math light computer science version of encryption. I'll just tell you, like this involves a lot of prime numbers and modulo arithmetic. Okay, so questions on that? Everybody see the power of a system that you can give away these public keys and have and be able to just put those out wherever you want on the net, and then people can use those to send you anything. Okay, but typically for efficiency, we just use that to transfer keys to each other because keys are very small, and then we use these more the more simple symmetric encryption to do the bulk encryption of data and things like that. Okay, the other powerful thing about using this two-stage technique where you have asymmetric to transfer the keys is that you can constantly change your symmetric keys. Okay, which is good because since they're out there, since the symmetric keys are getting out there, if somebody steals one, okay, if I steal a key like this Roman numeral 1, right, this symmetric key, if I steal that, anything that has ever been encrypted with it can now be decrypted using that key. Not just when you're transferring it. So if you're sending me a file, I can capture that file and store the encrypted file and then just sit and bide my time while I try and eventually steal the key. Okay? But when I finally get the key, I can decrypt. Okay, so changing these, every time you change a symmetric key, you've basically stopped how much can be decrypted with that. Okay? So these crypto systems are kind of these are a lot of the foundation of a lot of security in both operating systems and networks. Is a lot of these techniques are used to help implement some of the security concepts on these different systems. And here they go into a little more detail, showing you a relationship between a public and private key. Yeah.
What's the problem to decrypt the symmetric system? Where's the problem?
It just takes a long time. It's just performance. Because the math involved, or the calculations involved, for asymmetric encryption is very different from symmetric encryption. Okay? Symmetric encryption is, many orders of magnitude faster than asymmetric. Okay? Asymmetric encryption, or symmetric encryption, is often just very, very simple operations, like XOR, addition, stuff like that. Okay? It's usually very, very efficient, very, very fast. They get this to the point where you can do this in real time. Like with symmetric encryption, you can do things like encrypt a phone call while it's happening. Okay? And they typically also have other techniques, just kind of as, some background. There's actually two types of symmetric encryption. They have what's called stream ciphers, and they have what's called block ciphers. Okay? The one that is typical general use is block. Okay? Stream is usually for things like phone calls. But these are very fast. and you can do them in real time. Asymmetric involves a lot of factoring, prime numbers, multiplication, more complex things that take a lot longer. You're welcome to use asymmetric forever, like just for everything. It's just, it'll be very slow. There's also one other drawback, okay? Is using asymmetric, you have a tendency to use the same key for all of your communication. If your private key ever gets found, all of the things that you've ever, been able to decrypt with it can now be decrypted. Symmetric is very good for just creating keys whenever you want and disposing of them when you're done. Like typically, if you're doing like SSL, like with a website, you're using one-time symmetric keys that are just for that one session, and they'll change over time. Whereas you're probably, like the website is probably using the same asymmetric key for at least a couple years. Any other questions? And I mean, to me, security is a whole separate discipline that you can do in operating systems, architecture theory, that kind of stuff. Networks. That's what I used to do in the corporate world was information security. So, and you can do a whole career out of just focusing on security. Okay. So just a couple other points in this section. What we've seen so far with this encryption has been focusing on which of these kind of security attributes that we're trying to protect. What were the three? Anybody remember what the three things we're trying to protect with security are? CIA. What's CIA? C stands for confidentiality. I stands for integrity. And A stands for availability. Okay? Encryption is very, very good for protecting confidentiality, hiding data from people who are not supposed to see the data. Okay? But we have some problems still, even with a fancy system like the one we've seen here. Okay? We've, for the most part, protected ourselves from an attacker that we usually call a passive attacker. Okay, an eavesdropper. Okay, an eavesdropper is someone who can see the communication or data between two parties. Okay? We have not protected ourselves from an active attacker who can not only see what's going on, but also manipulate what's going on. Okay? Does anyone know what kind of manipulation we can do on this system to break it? How does a new attacker, usually called M, Mallory, okay? Assume M can alter any message between A and B, however it wants. How can it steal the data, the file? Okay, steal the key. Easy to say, hard to do. That's first of all, that's always the answer in any crypto system, is you can win by stealing the key. And that's by design, right? By design, all of the secrecy lies within the key. And also, what key? What? Which decryption? There are symbols up there. What symbol does M need to steal? Yes, it could steal 2.
But it's never in traffic.
Right. How would we steal 2? We'd actually go over to B, punch him in the face, and take 2. Okay? But it's never in traffic. So, no good. What do you steal to steal the file?
Yeah, he's supposed to be prime.
There's no B prime.
Not B prime, say 2 prime.
2 prime. Steals 2 prime.
Send a different thing. This version of P.
Okay, that's good. Okay, that's a step ahead. But my first question was, what key do we need to get to steal the data? I.
Or 1, sorry.
Roman numeral 1. That's the key we need to steal. Okay, now you're on track to steal key 1. So, you're suggesting that at the step when 2 prime is being sent, what does M do?
After 2 prime.
Okay, so first of all, we prevent 2 prime from getting to A. So what I'm going to do is I'm going to erase the line going from B to A, and I'm going to have M intercept 2 prime. What do you want to send out instead?
Send A to 3 prime.
Okay, so what you're saying is I'll generate 3 and generate a 3 prime off of that and send 3 prime. What will happen now?
What if I gonna be 2 prime? So
That doesn't mean anything.
About whatever A is sent now with the key 3 prime. Just B will
What is A sending? What is A trying to send to B?
the file.
No. Key. What key?
1.
Right, Roman numeral 1. A wants to send Roman numeral 1 to B. So, what did I do to send it? Before, I encrypted it with an asymmetric encryption. Okay? But, what do you notice about the factors going into this algorithm? 2 prime and I. Does A have 2 prime? No. What does it have instead? 3 prime, right? Right? So now A is encrypted, 1, right? 1 is encrypted with 3 prime. Your trick worked. You gave a different key instead of the public key from B. Now what will A do? Send this to B. So, do we let it send to B? What do? We intercept it. Right? And what do? We decrypt using 3. Okay? We're talking about the crypto systems. To do something, you need to tell me what we do. Okay? Saying I get the key. Well, we could have just said I get the key and not looked at any of these diagrams. Okay? We are looking at the mechanism. So we need to say the exact mechanism. So, I decrypt I1 using 3, right? And that will become what? Right? Just 1, the symmetric key. Now what do?
Can we stop there for a second?
Sure.
If M just wants to mess mess up the communication between A and B. It could just let A send 1.
If we're doing this, you could just stop communication altogether if you want.
You see what I'm saying? Though, if A sends what it thinks is or it sends 1 encrypted using 3 prime back to B, then B
We'll be able to do nothing.
So you effectively shut it down.
But if we're doing this, we could already shut it down without messing with any of the crypto.
Okay.
I mean, yes. I mean, that would mess with it, but they'd detect it. They'd see,
right.
Oh, it didn't decrypt.
But we're actually trying to get
Right. The key is, so far, no one notices what we're doing. So, I now have I1. What do I do now?
But we have to send the file.
I need to do something else, though.
Send B.
Right. I encrypt 1 using 2 prime. So what I do is I take 2 prime, send this, and create I encrypted with 2 prime. Then I send that up. Notice, we get back to looking exactly how it was supposed to, right? 2 will decrypt 1, and then we'll have the key. Perfect. Okay? So now, what will A do now? Encrypt the file with key 1, right, and send it. Now, we can just watch it go past, or we can intercept it again. But it doesn't really matter because the file, right, is out there with I. We can take a copy as well, decrypt it because we have I. So we just stole the data, right? Does anybody know that we stole the data?
No, of course, B will know because we can open it.
B can open it. B can open it. B can open it.
Can open it?
Yes. Show me why B can open it. That's why we did the clever step here. Encrypting I with the two prime and sending it. He actually has I.
Okay. So it's going to be the same key.
Yeah. Which is perfect. Nobody knows. What?
That's still dangerous.
Right. Nobody knows until what? Until we go away. Because then what will happen? They won't be able to communicate. They'll probably renegotiate keys. So, what's the problem here? Yeah, it's not a problem for M. M lucked out. Okay, the problem is this. When 2 prime came in, we had no way of verifying that that 2 prime was from the correct person. In other words, M was able to substitute another public key. This is an authentication and integrity issue. Okay, this is something where we don't want people to be able to alter data that's being sent. Okay, so authentication. Okay, constraining set of potential senders of a message. Okay, so what we're trying to say is that we want some assurance that the person sending a message is the actual sender. Okay? This actually needs to inherently be able to verify the integrity of a message. In other words, it needs to verify that the message was not altered. Okay? It doesn't really help us if we can verify that a sender is the sender if all the data that they meant to send was altered, right? What we need to verify is that a message sent is from who says they sent the message, okay? And also, is the message they sent? Integrity. Okay? So, here they're showing us some an algorithm. What is it doing here? Okay. What they're saying is that we have a function that takes a key, a message, and then it turns into some sort of piece of authentication. And this piece of authentication, the A, okay, needs to be able to, you need to be able to map this A, the message, and some sort of key to yes or no. In other words, yes, the person with this key sent it, or no, the person with this key did not send it. Okay? In the cryptography world, authentication is often done with what's called a digital signature. Okay? A digital signature has a different goal from the encryption that we've been talking about. The encryption we've been talking about, its goal is to what? Hide data. Protect confidentiality. A digital signature is to verify authenticity and integrity of a message. Okay? So, but outside of the digital signature world, authentication is also techniques that we're all probably even more familiar with, like logging into a system. What do we normally use? Username and password. Yeah, PIN, password, some secret piece. Okay? So, the idea is, if I give you a username and my password, what am I saying to the system? What's that? You're verifying that you have the secret for that user. And what does the system assume from there? Is that the authorized person that's assigned that user account is using that user account. Okay? Right? The idea is that if me, Steven, wants to log into a system, I log in using a user account. Right? That user account may be also named Steven, who knows? But the idea is that the system administrator, the person, the operating system, assigned me a user account. And the hope is that I correspond to that user account. When I'm in a shell, in a window, when I'm doing things with that user account, the hope is that I am the one doing it. I, the person. Okay? But what can the system actually only verify? By me logging into a system, is the system sure that it's me? What's that? Yeah, so it means I typed in the password. So what is the system actually verifying? Right. What the system is verifying is that you know the password. Okay? That the person operating this account has the password. That's not the same as the person is logged in doing stuff. Okay? So, the same idea goes for this encryption stuff. Encryption, the only difference is that instead of a little password that we type in on a keyboard, there's all this math involved. There's a lot more math than just a password involved with doing the authentication. Okay? But the idea is that the person who's supposed to be sending something is sending something. Okay? So with authentication, typically what you'll use is what's called a hash function. Okay? We've talked about hashes. The idea is you take what? You take data, I send it through a hash function, and what should come out? A hash. Okay, what's a hash? It's a fixed size piece of data. Okay, a good hash function will make it so that data that you send in, you don't know what hash value will come out. Okay, but you do know that it will always be the same for the same data. and that it will often not be the same as other data. Okay? When you send something through a hash function, what you're what the math behind a hash function is trying to say is you do not the original message, if you send it through the hash function again, it'll come up with the same hash function, and that if you slightly alter the message, it will come up with a different hash value. Okay? So what we typically do is we will hash a message or something that we want to authenticate, and then what we'll typically do is encrypt the hash value in some way. Okay? So we can do things like message authentication code, which is using symmetric encryption. What you do is you take a hash of the message, encrypt that hash using a key that only you and another person know. That other person can decrypt the encrypted piece, and what will come out? If I take a message, I send it through a hash function, what will come out? Right? So this will be what's called MD, is message digest. Okay? It's just an abbreviated form of the whole message. Okay. I now have a message digest. Now what they're saying here with a MAC, M-A-C, okay, is I will take a key. I will send that through a symmetric algorithm. What will come out? What will come out? Message digest encrypted with a key. I give this to someone, okay, and they also have the same symmetric key. That's a wave of the hand. Okay, they have the key as well. Okay, so the other person has a key. What do you think they do? And we just gave them this message digest encrypted. No, not yet. They get MD, encrypted with key. Send that through what? Symmetric algorithm. And what comes out? MD. Okay. Now, the whole point of this technique was to verify the authenticity of a message. So what do you think we also got in addition to the value MD encrypted with key? Well, we got the key, yes. What else? We know the hash function and we know the symmetric algorithm. What else did we get as the receiver? What was the whole purpose of the exercise? To get a message and verify its authenticity. In other words, that it was sent by a particular person and it wasn't altered. So what else do we have? It's tricky. What else did we receive as the person trying to verify this information? What are we trying to verify?
The real one?
We're trying to verify that the person who says they sent the message, and that the message was not altered. So, what we've received is some sort of message authentication code. We have the key, and like I said, that's just, trust me on that. You got the key. You have the message authentication code. You know all the algorithms. What's missing? The purpose of a message authentication code is to verify that the sender of a message both sent the message and the message was unaltered. On the other side, I have a media authentication code. or a message authentication code. I have a key. I have a hash algorithm. I have a symmetric encryption algorithm. What is missing? Look at the symbols on the left and the symbols on the right. What symbol is on the left that is not on the symbols on the right? M. What is M? The message. What is the goal of this algorithm? To verify that the sender of a message is the sender and that the message was unaltered. So we use a message authentication code. There's a word that is in common with all of those things I said, and that is message. We need a message. If we don't have a message, we don't have anything to do. Okay? So the other thing we have as the receiver is the message. Okay? Was the message encrypted? Was it hidden from anyone? No, we don't care about that. What we care about is what? That the sender who sent the message is the actual sender and that the message is unaltered. I repeat things because that's important. All right? So, we have a message. Now, what we also have is a message digest. Have we verified the things that we want to verify yet? No. What do we still need to do? Put what? Put the MD into a hash function. No. We cannot go the other way through a hash function. That's something I forgot to message. A hash function is one way. Okay? If a hash function, but in my defense, a hash function could not possibly go the other way. If you do, you have created perfect compression. Okay? Because if you can send a variable size message through a function and get a fixed size block that comes out, if you could go the other way, that means what you're saying is that this fixed amount of data can get me back to any size original data. What you're saying is that hash value that comes out is all that is needed to store any amount of information. Does that sound true? No. So you can't go the other way. So I cannot send the message digest through a hash to get the message. I send the message back through the hash. What will come out? We'll call this MD prime. Now, how do I verify? If MD, that's correct. If MD and MD prime are equal, tell me what we've verified. Say something, please. Say something. Say something that I've said over and over and over. All right. And what? And then what hasn't been altered? Okay. What we've verified with this is that the message has not been altered. The other thing that we've verified is that the other person who has K is the one who sent it. Do you see how this is different from the other encryption we were doing? The other encryption, our goal was to hide the data. What we've done in this one is we've verified two things: that the other person with the key sent it and that the message wasn't altered. How have we done that? What would happen if the message was altered in transit? So, our sender was sending M, someone came in and substituted M prime. What would change? Okay, why? Because M prime is now what goes through the hash function. It comes out and MD prime comes out. These cannot be equal. Why? because that was one of the basic functions or the basic attributes of the hash that we said it can do. Is that if you alter a message, it should alter the hash. Yeah.
So M has to be known by this side before even send or anything. Because the reason is that M is not going through these steps, the communication.
M has to be
The beginning M.
We just send it.
So what about the middle person grab and he change and he put in actor and send it to?
What does he not? Okay, so what does he not have? Key. If I intercept M and alter it and create M prime, what would I need to do? I need to send it through a hash, create an MD, encrypt that with a key, and create MD encrypted. I can't do that. I don't have the key. This MD encrypted with a key is uniquely tied to both M and the key. Okay? What was the magic hand waving that I did in that one? Is that both sides have the key. Okay? This type of authentication is typically used to verify the authenticity of messages being sent, or like the bulk data, the file. It verifies that the file wasn't altered, things like that, because we could exchange the key, the K, with other means, like asymmetric encryption techniques that we saw before. But we still have the same problem that we originally started with, and that's what if somebody substitutes another key? So, digital signature is kind of is another level of signing, where you actually sign using, where you encrypt these things using asymmetric encryption. Okay, it's actually done in a very counterintuitive way. Asymmetric encryption. How do we usually encrypt and decrypt between people? Okay, how do I use the public key and private key? And then I will do what? Encrypt using encrypt using public key, decrypt using private key. Okay? I'm the only one allowed to hand wave. Okay, I'm the only one who can say, magically the key went over here, or magically we've decrypted. All right? If you're going to tell me that something was encrypted or decrypted, you need to tell me what key was used, and that kind of thing. Okay? So, and this is what we'll kind of end on. I think. Typically, you encrypt with a public key, decrypt with a private key. Digital signatures do the opposite. Okay? So, if we're doing the opposite, what do I mean by that? Encrypt with private key, decrypt with the public key. Now, can I still do the same things that I was doing with the other technique of encrypting with the public key and decrypting with a private key? What was my goal of encrypting with a public key and decrypting with a private key? No. No.
Only the receiver can actually translate.
Only who can decrypt the message. Who can decrypt the message? No. Well, I'm saying in the original scheme. The receiver, because okay, the holder of the private key can decrypt. Okay? So if I were to do this opposite, where I encrypt with the private key and decrypt with the public key, who can decrypt things? Anybody holding the public key. So can I use this to hide data? No. Okay? What do you think I can use it to do? Authenticate data. How?
Private key, only the person is authorized to send the messages on the person. Nobody else.
What is something encrypted with the private key says what? That the person, the holder of the private key, is the one who encrypted this particular piece. Who's the only person who has the private key? Well, the sender or the original person. Right? The person who wants to be authenticated. So, do it. What are we trying to authenticate? What is the goal of authentication? And this should be like quick at this point. The goal of authentication is to what?
The specific person.
We're trying to verify what?
You can say verify the sender. That's shorter.
Verify sender? No. No, that's not that because that's insufficient. We're verifying the sender and verifying the message. All right? We're verifying that the message wasn't altered and that the sender is who they say they are. Those are the goals. How do we do that? With this. What do I have? I have a message. I have a private key. I have a public key. And I have algorithms galore.
It's a regular encryption.
We are trying to authenticate to another person over here. A. B. I want to be able to send a message to A, and I want B to be able to verify the sender and that the message was not altered. So, B is trying to verify that A sent a message and that the message is not altered.
So encrypt them.
Encrypt M. That's a lot of hand waving there.
Using private key.
Encrypt the whole message using the private key. Okay. So, go on. What's that? Say exactly what happens.
He received the message.
Receives M.
M.
I'll give you that.
With A prime.
What?
1 prime.
1 prime. I'll give you that. 1 prime you can do. Decrypt that?
Yes.
No, that's not encrypted. Garbage would come out.
Yeah, these are send it send M1 across the line. Get M. And you should already have M. Yeah,
Very inefficient. Why?
already have n, compare it with this thing, it should be verify the sender and the message.
I agree. We should notice something different from what we saw before.
We have hashed.
And why waste some perfectly good algorithms, right? We haven't hashed anything. It's no fun.
Right, so we got M,
M.
and we hash.
What comes out?
ND.
MD. What do we do?
Symmetric encryption.
Asymmetric encryption with
P1.
what comes out? MD encrypted by 1. Now what do we do? What does B get?
ND.
Gets what? B gets what?
ND1.
Okay, so we sent B MD encrypted by 1. What else does B have? M and 1 prime. M 1 prime. What comes out?
And ND1 encrypted by 1 time.
You're saying take 1 prime and MD encrypted by 1, decrypt it with asymmetric. What comes out? MD prime. And then what? Compare the two. Same thing that we did with the symmetric, only now we're doing it with asymmetric. What's very good about this system? What pieces of data does B have?
Name and
1 prime, which is a public key. Do we care who gets 1 prime? Anybody else who steals 1 prime, all they can do is verify the authenticity of messages that I've sent or encrypt data to me. Neither of those are dangerous. Well, not dangerous in the sense of what we're trying to do. This is the basic idea behind digital signatures. Okay? Whether you know it or not, you use this often. All right? Every time you go solar, every time you go to Bank of America, every time you do any kind of business transaction on the internet, chances are you are doing something along these lines. Because, let's see real quick. Yeah, just kind of as a parting words, this really hasn't solved much of our problem. Okay? The reason being is that the reason it hasn't solved much of our problem is because people can still give out the wrong public keys, right? If I can substitute in 2 prime instead of 1 prime, I can now alter messages, sign them with 2, and then they'll verify okay, even if I alter the message. Right? I've changed the problem. I've changed the problem to I have to prevent people from altering 1 prime. Right? But how do I verify that 1 prime is not altered? What, do I sign 1 prime? Well, what am I going to sign 1 prime with? 2 prime? Well, then how am I going to get 2 prime out of it? What am I going to sign? Should I sign that with 3 and then distribute 3 prime? Okay, the answer is somewhere, something has to be verified. Okay, the typical technique is using what's called, these are called digital signatures. They're also related to this is called digital certificate. Okay, a digital certificate is a way of putting all this information into a nice package that you can use to sign things and whatnot. Okay, typically what you'll use is what's called a certificate authority. Okay, these things like VeriSign and places like that where you see, when you're on the web, you have your little padlock and you can double click it and it shows you VeriSign says it's okay. You know, it's like you go to Amazon and it says, you know, VeriSign digital signature or whatever, confirmed. Okay? What they do is VeriSign will be a certificate authority where if everyone can trust VeriSign's public key, their one prime, what they'll do, all VeriSign does all day is sign other people's keys. So what does that mean? If they can sign a key, what they're saying is that I, VeriSign, say that this key belongs to this person and has not been altered. So then, when you get another user's key like my key, you can at least be sure that VeriSign thinks that that's my key. And then, if you can verify my key, then I can send you things that are signed with it whenever I want from there on out. So the idea is you've consolidated all the things that you need to verify just down to VeriSign's or some other company. You've created, that's the only thing you need to verify. Everything else from there can be signed using these techniques. But you need one starting place, at least. And that's usually a commercial company like Thought or VeriSign. There's a bunch of different companies that do this. Okay?
So in our example, what's the actual digital signature?
The message digest encrypted by the private key. That's considered a signature, a signing of M. So typically it'll be seen as M with the MD encrypted at the bottom. That's kind of like, if you think of it as signing, it's like a contract and then a signature at the bottom that ties it to the contract and the signer. So, that's your crash course in cryptography. Cryptography is a powerful, powerful tool for doing security and protection throughout operating systems, networks, everything. And it's also a very, very powerful skill to have as far as seeing the techniques. Because these types of techniques, these operations, these are protocols. So if you're doing anything that's involving protocols, distributed algorithms, anything like that, seeing these types of things in action helps because you kind of get the feel for how protocols work. Okay? You want to make sure that you only have this data and that, you want to be sure where the data is, who has what data you don't want other people to see, what algorithms you have on both sides, make sure they're matching. Okay? Okay.
So